So now that we've got a good idea of how the LED circuit is going to be built with the LED and the resistor and a power supply with ground and positive 5 volts, we want to actually implement it here with an Arduino and a solderless breadboard. So I've arranged the two of them with the Arduino on the top and the breadboard on the bottom. Remember, we have the trough of the breadboard that divides it into a top section and a bottom section. And then we have the ground bus at the bottom and a power bus at the top. The Arduino is currently not plugged into the computer, but once we plug in USB power here, then the ground and 5 volt pins on the Arduino will be supplying power, and they will in turn be distributed to these two rails, top and bottom. So we're going to start with the wiring for that. And what I've done is I've twisted together a red and a black wire just to make them neat in the final arrangement. And I'm going to put the ground into one of the two ground positions. That's the black wire. And I'll put the red wire into the 5 volt power there. So like so. And then I'll bring them around to make sure that I put the black into the bottom ground bus and the red into the top power bus. So now ground and power from the Arduino are being brought down into the breadboard's power rails, top and bottom. And if we were to plug it in, then all of these connections on the top would be 5 volt power, and all of these connections at the bottom would be ground. But first, let's build a circuit with an LED. So here's our light emitting diode. It's a little plastic package with a couple of legs. Notice that one leg is longer than the other. And so I'm going to arbitrarily just stick it into the breadboard with one leg below in the first column and one leg above in the first column, over the trough like so. I'll push it a little bit out of the way so you can see. So now, because I have plugged into the bottom here with this lead, these other 4 holes are now exactly electrically the same as the bottom connection on the LED. And the same at the top, because I'm plugged in here, these other 4 holes are electrically the same as the top of the LED. And the trough in the breadboard separates top from bottom. So step 1 good, we have the LED from the drawing. Next we need our 330 ohm current limiting resistor, which is an orange-brown. And I've already pre-bent that so that we can plug one into the bottom column and the other end into the ground bus, like so. So now the connection will come from the Arduino to the ground bus, through the resistor, through the LED, to this top column, and then it goes nowhere. So what we need to do to complete the circuit is we need to connect from any hole in this column to the power bus. And that will give us our basic powered LED. So I'm going to use a little short red jumper cable. I'll just plug in arbitrarily anywhere there and anywhere there. So now I have a power connection and a complete circuit once I actually supply power to the Arduino by plugging it in. So let me hold that down for a second, and I will plug in the USB cable. And now the Arduino power light has come on, and the LED has not illuminated. So what's the possible problem? Well, when we put it in, we arbitrarily put it in one direction. Remember, the light emitting diode is just that, a diode that emits light. And a diode has to be in the circuit in the proper polarity. We put it in randomly for top and bottom, and we might have chosen wrong. So let's see if that's the issue. Anytime we make a change to a circuit, we want to power down the Arduino. So I'm going to unplug it. And then let's pull the LED out and just turn it 180 degrees, and I'll plug it back in. So now the long leg is at the top and the short leg is at the bottom. And now I will plug the Arduino back in, and lo and behold, the LED lights up. So that was indeed the problem. We just had the polarity wrong on the LED. So now we've made a circuit from 5 volts to the 5-volt bus at the top, through this wire, through the LED, through the resistor to ground. And we do not have a short circuit because there is a resistor between our 5-volt side and our ground. And we've implemented that schematic drawing in a live circuit form. So congratulations, you have now converted your $30 Arduino into a 25-cent battery. Because all this does is light the light continuously. It doesn't do anything that we can program. And the whole point of an Arduino is to program things. So let's unplug the Arduino and make one simple change. We're going to remove this wire. And I used a red wire because it was a 5-volt power supply, and red always means 5-volt power supply when you're wiring up things with a breadboard. So I'm going to switch to this yellow wire instead. I like yellow for input-output pins. And up here on the top, here's pin 0, pin 1, and pin 2. I'm going to go to pin 2 on the Arduino's digital pins. And instead of going to the power bus, because that would be bad, I'm going to go instead to where we were plugged in before, that top column. So now the path is, we have ground, which comes through to here, to the ground bus, through the resistor, through the LED, and then our connection goes back not to power, but to pin 2. So now under program control, we can decide that pin 2 will supply 5 volts or will not supply 5 volts. And we can turn the LED on and off. So I'm going to go ahead and plug in the Arduino. And of course, the LED does not light. Why? Because we haven't programmed it to. What the Arduino is actually doing is this microcontroller chip right here is not running no program whatsoever. It's important to realize it's running whatever program we loaded into it last. And because the last thing we did was our tour of the Arduino software where we downloaded the ASCII table program. If I click the serial monitor, lo and behold, that's what our Arduino is doing. It's printing out serial data to the serial port. So the first thing we need to do is to write a new program from scratch. And here's our empty sketch ready to go. So we're going to start to do a little typing. We need 2 things for an Arduino program to run correctly, 2 functions to be defined. So I'm going to type the word void, and notice as soon as I type it, it turns orange, which means in the Arduino environment that that word is a reserved word. It means something to the Arduino software. I'm going to do a space, and I'm going to type the word setup. That also turned orange. Interesting. I'm going to type a left and right parentheses, a return, a left curly brace, a couple returns, and a right curly brace. Then I'm going to type void, turns orange again. I'm going to type the word loop, left and right parentheses, left curly brace, right curly brace. So this is the absolute minimum program you need to be able to upload to an Arduino. What it does is it defines 2 functions. One function called setup, and the setup function runs once every time the Arduino starts up from scratch, or if you hit the reset button on the Arduino, or if you run the serial monitor. After setup has run, then the next function, loop, runs. And loop runs, as the name implies, over and over and over again forever until you power the board off or reset it or run the serial monitor. So setup runs once, loop runs forever. Now the keywords void before loop and setup just tell us that the setup function and the loop function do not return any value when they're done running. We'll see other functions later on that might return numeric values or character values. But void just says no value is going to come back from setup when it's done. The left and right parentheses tell us that setup and loop do not need any information to do their job. So they do not receive what are called arguments. So imagine a math function that computed x raised to the power y. That function would need to know x and y. And so we would have information inside those parentheses telling it that there's a variable x and there's a variable y, and then down in the body of the function is where we would do the actual calculation and return it. And we would have had to define ahead of time how we were returning that value. But because setup and loop are built-in functions that the Arduino has to have, they don't return anything and they don't take any arguments. So let's go ahead and upload this sketch. So first of all, we'll see if it compiles. Yes, it is done uploading. Great. Now we know that there's nothing happening on the Atmega 328 chip in the Arduino. It is sitting there doing absolutely nothing thousands of times a second because loop is still running. Setup ran once and did nothing. Loop is running thousands of times a second doing absolutely nothing. So now that we've got it doing nothing, let's get it to do something. What we want to do is we want to use digital pin number 2 to turn the LED on by outputting 5 volts through this wire. How do we do it? Well, first of all, note that these are digital pins. They're not digital input pins. They're not digital output pins. They're just digital pins, which means pin 2 can be an input or an output depending on what mode we put it in. So the first command we're going to type in the void function does just that. It's pin mode, and notice that the P is lowercase, the M is capital, and as soon as I type it correctly it turns orange, which means the Arduino knows that that's a reserved function. And it's going to get a couple of parentheses and then a semicolon. So there are going to be some arguments in here that tell pin mode what to do. So I'll click back in here and I'll type 2, comma, and then in all caps, output. And as soon as I type output correctly, it turns blue, meaning that's another type of reserved keyword, which is a pre-declared value. So output means something to the Arduino environment as well. So we're basically saying, hey, pin 2, you're going to be an output this time around. And then the next thing we need to do is we need to write some sort of value to that new output pin we've defined. And we do it this way. Digital write, write is capitalized, left and right parentheses and a semicolon. I'll do this a lot so that I don't forget a parenthesis. And then I'll click back in and I'll say 2, comma, and in all caps the word high. High is the same as a value of 1, which is the same as 5 volts in this instance. And when I've got those two things, pin mode, pin 2 output, digital write, pin 2 high, I click upload. Now we have 872 bytes. We are done uploading. And notice, lo and behold, our LED lights up. So the same as we had before, an illuminated LED, except we've done it under program control. And if I want to reach up here and click the reset button, I can rerun setup. And as soon as setup finishes, the LED lights up again. Great. Well, something we turn on, we can certainly turn off, so let's do that. Let's type digital write 2, comma, guess what it is, low in caps. Should have orange for digital write, should have blue for low. And let's go ahead and run this and we'll see the light turn on and off. We've uploaded. Maybe we missed it. Let me go ahead and upload it again just so you can see it turn on and then off. It's not turning on and off. What's happening? Here's rule number 1 of programming a microcontroller or a computer. Computers and microcontrollers are very, very fast. So it did what we told it to. It set pin mode for number 2 to output. It wrote the digital high, which turned on the light, and then a fraction of a second later, it wrote a low value, which turned it immediately back off again. It happened so fast that we as human beings could not see it. So what we have to do is we have to introduce a delay. so that we can see the light being on before it gets turned off. And yes, there is a function called delay. And that function takes a value in milliseconds, so 1,000 milliseconds will be 1 second. So we're going to set the pin mode, we're going to turn the pin on, which turns on the LED. We're going to wait 1 second, turn the pin off. Let's go ahead and upload that. The light turns on, the light turns off. Awesome. So we have programmed the light to blink on and off. So now, we've done this in setup, which means it happened one time. What if we move some of this down into loop? We don't need to set the pin mode over and over again. We only have to do that once per program run. So let's select this, exit from there, and paste it down here. I'll clean that up a little bit. Now, of course, we should be able to run this and see the light blinking on and off, correct? Let's compile it. Here it goes. There's the light blinking on and staying on. So what's happening? It doesn't blink on and off. Even though thousands of times a second it's going through this loop of turning it on, waiting, and turning it off. Rule number 2 of programming computers. They do exactly what you tell them to do. What exactly did we tell it to do? We said turn the pin on high, wait for a second, turn it on low, and then immediately loop back with no delay whatsoever to the beginning where you make it high again. So the LED's on, wait a second, off on, wait a second, off on, wait a second, off on, wait a second. So to our human eyes, that looks like it's continuously on. We have to give it a second delay so that we have time to see the fact that the light is off. So we'll type another delay 1,000. And let's go ahead and upload that. Lo and behold, the standard Arduino blink sketch that every person who does an Arduino tutorial shows you. I've just showed it to you this slightly more complicated way, piece by piece, but it means that you now understand exactly what each of these lines are doing, why we need each line of code, and what happens if you don't think things through properly. What might go wrong. Now that we have things running properly, we can play around with it a little bit. For instance, these two values don't have to be the same. What if we made one 250 and one 1,000? So a quarter second on and 1 full second off. And we just get a different blinking pattern. So you can play around with all sorts of different patterns in the blinking. Let's make this one be smaller. Actually, let's make both of them be smaller at the same amount. So we'll take them down to 250 and see what a quarter second on and off looks like. And we should get a pretty fast quarter second flash. Let's go down to 100 milliseconds, so 1/10 of a second on and off. See what that looks like. A much faster blink. And you can imagine the coffee pot designers of the world, or people building interfaces to things like thermostats, if you wanted an error message, trying to find just the right blinking pattern that communicated something to a person. And see how much faster it is to change a couple lines of code than to rebuild a resistor capacitor circuit that would do the equivalent of this in an analog domain. Because we've got the power of a microprocessor here, we just make a couple quick changes and we get a completely different behavior. So let's keep going. Let's go down to, say, 50 on each. 50 milliseconds. Notice that obviously as the delay is shorter, the blinking is faster. And what we're interested in is at a certain point, and this actually probably shows up better to the naked eye than it does to the camera. At a certain point, the on and off is so fast that it looks continuous. In fact, in the room with me, that looks like a continuous LED. There's still a slight blinking you see because of the video camera. So at a certain point, we get back to the point where things are happening so fast in the computer that they look continuous. So what I'm going to do is I'm going to set this to be a 1. I'll set both of them to be a 1. So 1 millisecond on, 1 millisecond off, and it looks like a completely solid LED for all intents and purposes. Let's start to make this second value, when it's off, larger. So now it's on for 1 millisecond and off for 2 milliseconds. It still looks on to me. Let's go to on for 1 and off for 4. Yeah. At no point do I see a blinking pattern here, but, and it may be hard for you to see on the video camera, but I can definitely see it in the room. As I increase the amount of time it's off, I get to the point where the LED looks dimmer. So that looks like it's barely on to the camera. It looks probably about a quarter of the brightness it looked when it was fully on. So that's on for 1 unit of time and off for 16. 1 millisecond on, 16 milliseconds off. And if I go back to 1 and 1, you'll notice a considerably brighter LED. So this technique of varying the amount of time the light is on and off is what we're going to use in the next video, so that instead of just having the light completely on or completely off, we can use the microprocessor to simulate an analog write. So we can't actually truly write an analog value to this LED. So we can't send it 3 volts or 4 volts. We can only send it 5 volts. But there's some built-in circuitry magic that happens in the Arduino, in this microcontroller, that uses something called pulse width modulation to make it look as if we're sending a varying voltage to the LED. And that's what we're going to look at in the next video. So for now, let's go back to, let's say, 500 on and 500 off, and we'll end the video by simply enjoying a beautiful blinking LED. There, I think you've earned that.